Now, this definition is equivalently to the original definition of uniform convergency. Let us prove this theorem or whatever it is. So first, let us understand the question. So we have a sequence of functions defined on some subset of R. So this A is actually a subset of, let me write it, real numbers. And for flexibility, let us assume that we have smaller subset B, and our sequence of functions are uniformly converging to some function on B. Okay. Now we are going to prove that this supremum of this difference is gonna be 0 when n goes to infinity. Okay. First assume, okay, from left to right, assume fn's are uniformly convergent to f. Now it means that for any epsilon bigger than 0, there exists some natural number, let me call n0 in natural number, such that if these little n's are bigger or equal to n0, then fn x minus fx is less than epsilon for all x in B, since it is uniformly converging on B. So using the definition of supremum, okay, let us now look at this inequality. We have some numbers, difference of some numbers, right, for some fixed x and n. So they are always less than epsilon, okay, for any x. So if you are going to write this set supremum, look at this x are changing. So by definition of supremum, these numbers are still less than epsilon, right? Because supremum means it is the least upper bound. If you have some upper bound for any x, it means that supremum also will be less than epsilon. Okay, then by definition of supremum, we have also, since it is denoted by dn, less than epsilon. Okay, but since it is an this is strict, so it is also strict, so there is no problem with that, I guess. Yeah, no problem. So, but also the definition of limit, okay, so consider this, every number is real number, right? So we are taking some supremum of real numbers, so this is also a real number, and since this epsilon was arbitrary, and we have some n0, and these kind of things are satisfied, so it means that this dn is also less than 0. Of course, this is positive because everything is in absolute value formation. So by equivalent definition of limit, it also means lim dn when n goes to infinity is 0. Okay, so this side is okay. Now let us prove the other part. Now conversely, assume that this dn is 0. Okay, the limit of dn is 0. Assume limit n goes to infinity, dn is 0. It means that I'm also gonna write the definition of limit in this case, so that we can check, we can pull back our definition for this uniform convergence. Now let us, okay, let epsilon be given, okay, because I want to prove the uniform convergence part. Let Hadi let me write it on white. Let epsilon be given. By the definition of by this part, we have some n0 in natural numbers such that if n is bigger or equal to n0, we have dn is less than epsilon. Okay, now what is dn? I'm gonna expand this inequality, but I'm gonna add another inequality here. Okay, let me start with fn x minus fx, okay, less than supremum of fn x minus fx or x in b, okay, because this is the definition of dn and it is by assumption less than epsilon, or the result of the limit. Okay, after that point, so for sufficiently large n's, I mean this n's are bigger than n0, this is happening, so it means that this is always less than epsilon for any x, right? Because we don't have any assumption on x. This is happening for any x, right? Because for any x, this inequality holds. Okay, holds for any x, because we are taking the supremum for every x in the set B. That's why there is no problem. So we have the required generality, right? Because in the definition of uniform convergence, this x is okay, this n is independent of the choice of x. So this n should satisfy for all x's in the B, in this case also. So by definition of uniform convergence, this is indeed the case, right? So let me finish. So indeed fn's are uniformly converging to f on B. Şimdi bunu Türkçe açıklayacağım, sonra İngilizce açıklayacağım diğer videoda. Şimdi bu sorunun anlamı ne? Bunu anlamak için ilk önce uniform convergence ne demek, onu biraz anlamamız lazım. Uniform convergence ne diyor? Diyor ki senin elinde sequence of function'lar var, yani fn'ler var. Değil mi? Bu fn'ler bir yere yakınsıyor diyor, işte f diye bir fonksiyona. Şimdi bu fn'lerin hepsi real eksiste tanımlı fonksiyonlar değil mi? Yani nasıl fonksiyonlar mesela? Şöyle bir grafikler düşünebilirsiniz. Mesela bu f1 olsun. Değil mi? Şöyle bir şey f2 olsun. Şöyle bir şey f3 olsun. Renk değiştireyim biraz. Şöyle bir şey f4 olsun. Falan filan. Sonsuza kadar gidiyor. Şimdi diyor ki eğer bu sequence'lar, bunlardan sonsuz tane var değil mi? Hani çünkü birden sonsuza kadar gidiyor. Bunların hepsi bir tane fonksiyona yakınsıyor mu demek ne demek? O şu demek. Şimdi yeni bir grafik çizeyim. Şimdi onu da morla göstereyim. Diyelim o yakınsadığı fonksiyon f diye bir şey olsun. F, tamam mı? Bu şu demek. Eğer bu fn'ler f'ye uniform olarak yakınsıyorsa bu f'nin etrafında bir tane tüp var gibi düşünebilirsiniz. Böyle bir tane tüp çizin. Şöyle bir tane tüp çizin. Öyle ki bu n eğer büyük n'den, hani tanım neydi uniform convergence'ın? Epsilon bigger zero verilsin. There exists n, değil mi? Hatta n0 olsun bu. Such that if n bigger than n, then fnx eksi fx less than epsilon for all x in the domain. Domain neresiyse. Şimdi buradaki büyük n'den, burası n0 olacak bu arada. Büyükken bu küçük n'ler ne yapacak biliyor musun? şuradaki n'ler, fn'ler hep bu tüpün içine düşecek. Yani mesela şurada bir tane fn artı 1 olsun. Fn artı 1 bu tüpün içinde olmak zorunda. Fn artı 1, büyük n artı 1. Çünkü o n büyük n'den büyük içinken bu doğru oluyor. Mesela fn artı 2 nerede olmalı? Başka bir şekilde olsun, şöyle olsun. Ama yine de bu tüpün içine düşmesi lazım. F büyük n artı 2. Böyle yine işte bundan büyük bütün n'ler için şu fn fonksiyonlarının hepsi bu tüpün içinde yer alması lazım. Değil mi? Bu uniform convergence'ın mantığı bu. Hani şunu da çerçeve için alayım. Bu uniform convergence'ın mantığı. Tam bu soru ne diyor peki? Bu sorudaki bu şey ne diyor supremum? Supremum da diyor ki senin bir tane yine fix f'n var. Değil mi? Onu da yine morla yazayım. Bir tane f var. Şu f. Şimdi fn'ler bir tane fn çizdim diyelim şöyle. Onu da kırmızıyla çizeyim. Fn. Diyor ki her nokta ne demek? Bir tane x alıyorum şurada arbitrary. Değil mi? Şurada x alıyorum. Burası x ekseni. Burası y ekseni falan filan. Diyor ki buradaki x noktası için şu ikisinin arasındaki fark. Şu ikisinin arasındaki farkların hepsini alıyorum. Mesela buradakini alıyorum. Sonra buradaki farkı alıyorum. Değil mi? Şurası. Bütün farklarını alıyorum ve bunların supremumunu alıyorum. Yani buradaki bu iki fonksiyonun grafiğinin arasındaki mesafelerin hepsinin en büyük şeyini alıyorum, supremumunu. Sonra buradaki n buraya bağlı ya. N'nin limitini aldığımda bu supremum sıfıra yaklaşıyorsa ne demek bu? Buradaki fn'ler arasındaki mesafe sıfıra yaklaşıyor demek. Ama her x noktası için. Dolayısıyla bu tanım hani şuradaki noktasal şey bir anda anlık olarak, yani bu aslında metrik diye de geçiyor. Yani iki fonksiyon arasındaki metrik diye de verilir, şu supremum metriği diye. Ama onu daha görmedik. O mantığa yarıyor yani. Buradaki bütün noktaların arasındaki farkları al, supremumunu al. O supremum sıfıra gidiyorsa o zaman bu iki fonksiyon, bu f fix zaten. Fn'ler f'ye çok yaklaşır demek. Ya da orijinal definition'da ne demek? Bütün x'ler için buradaki tüpün içine düşüyor demek. Yani buradaki definition'la bu orijinal definition aynı şey demek. Hani supremum tanımında bütün mesafelerin supremumunu alıp limitini al. Eğer sıfıra yaklaşıyorsa o zaman fn'lere çok yaklaşacak. Orijinalde ne diyor? Orijinalde de aynısını diyor. Hani başka bir şekilde yazılmış gibi düşünebilirsiniz. Okay, to be able to understand the question, let us first revive the definition of uniform convergence. What is uniform convergence? For any epsilon bigger than 0, there exists some n0 in natural numbers such that if n is bigger than n0, then f of nx is subtract from f of x is less than epsilon for all x in domain, wherever the domain is. So let us expand this definition. So let me make a graph. Since everything is in the real axis, they have a graph, right? They have some graphs. So let me fix with purple. So let us call this is your f. And of course, I'm assuming that fn's are uniformly converging to f. So it means that we have some tube around this f. Okay, I'm talking graphically, pure graphically, okay, geometrically. So let me draw some tube. Okay, for any epsilon given, the diameter of this tube is epsilon. Okay, this diameter is epsilon for any given epsilon. So the definition says that for bigger values of n, so if you get bigger and bigger in this index, your fn's must be inside of this tube. Okay, for example, let me draw some fn's. For example, let me draw some, for example, f bigger n0 plus 1. It should be in this tube by definition, okay, because of this assumption. Okay, let me draw something else. fn0 plus 2, etc. Since every n bigger than n0, for this fn, they should be in this tube, okay? They cannot go out of this tube. This is the definition of, this is the geometric meaning of the original definition, okay? Now, let us analyze also this definition of supremum, okay? Let me also draw some graph. Let me fix f also. Okay. So let me draw another fn. Okay, this is fn. So for fixed n, okay, let us consider this supremum. Let us try to understand what does it mean. Okay, for each x, okay, for each x, I am calculating the difference in length, and I am taking the supremum at the end. For example, fixed x, okay. So let us consider this length. So I am taking this number inside of my set, okay. So let me consider another x, for example, here. So let me x1. So this is another length, right? So let me consider this length, this length, this length, all possible lengths, okay? Then after you are calculating all possible lengths, I mean this set without supremum, so you are taking now supremum. If the supremum, okay, is, okay, what does it mean? What is the meaning of the supremum? The supremum in this case is the largest length for some x, okay? For example, this is the biggest one, biggest length between these two graphs of these functions, okay? This is the biggest. If this biggest value approaches to 0, it means that this fn's should approach to f, or equivalently they should be inside some tube for any given epsilon. That's why these two definitions are identical, okay? This is the meaning of this question. So this is my question. We have sequence of functions fn's and sequence of gn's. They both uniformly approach to some functions f and g on the fixed sets A. So I'm gonna prove that this new sequence fn plus gn, they are just pointwise sum of each x, approach to some of these two functions. So it is very basic. So what is my aim? My aim is to show fn x plus gn x minus fx plus gx is less than epsilon, okay, for all x. My aim is x a if n is bigger than some n0, I don't know what it is, and for any given epsilon bigger than 0. Okay, this is my aim, right? But using the triangle inequality, I'm gonna manipulate this absolute value using these two assumptions to reach the same. So, okay, let me continue. Now, this was my aim, okay? So, it is unofficial. So, let epsilon be given. So, I am fixing my epsilon. So, since fn's are uniformly approaching f, we have some n1 in the natural numbers such that if n is bigger than n1, we have then epsilon over 2 is bigger than fnx minus f for any x. Why it is epsilon over 2? This epsilon is fixed at the beginning, right? It can be 2, 3, 4, 5, whatever it is. It is given. But since this is this fn uniformly approaches to f or converging to f, I can change this epsilon because it is up to me right now, right? This, by the way, this m1 is dependent on epsilon over 2, not on epsilon. Okay, so this epsilon is given by arbitrarily because I'm gonna prove this statement, not this. This is already assumed. Okay, so that's why I can write anything I like, but this m1 is dependent on this epsilon over 2. Similarly, since GNs are uniformly approaching to G on A, we have n2, let's say, in natural numbers, such that if n is bigger than or equal to n2, then epsilon over 2 is bigger than f, not f, we are talking about g's, gnx minus gx. Okay, for any x. Now, can you guess what is my n0 is? Since this is, by the way, okay. Since this n1 is making this inequality for sure, and this n2 is making this inequality for sure, if I choose the biggest one, every inequality would be satisfied, right? So that's why now I'm proving my aim. Choose n0 max n1 n2 if n bigger or equal to n0, or the max of n1 n2, whatever. So then f n x plus g n x minus fx plus gx, okay, is less than, or let me just manipulate it first, f n x, by the way, I am rewriting this or this, okay, minus fx plus g n x minus gx. So by triangle inequality, I have f of n x minus f of x plus g n x minus gx. But since this n is bigger than n0, and n0 is maximum of this n1 or n2, so these two inequalities must satisfy. So this should be less than epsilon over 2. This should be less than epsilon over 2, right? Less than epsilon over 2, less than epsilon over 2. So in total, everything is less than epsilon, as desired, for any x, by the way, for any x, because if you remember, everything is happening for any x. So it is finished. For the second part, I mean this, is it true that fn multiplied by gn is uniformly converging to f multiplied g on A? So I have a counter example. Consider the following functions. Consider fn x 1 minus 1 over x 1 over n, and consider g of n x, which is a constant in terms of n, always 1 over x squared. So since every function is just an element in the sequence, this is a constant sequence of functions, right? So this is always for every n, this is just 1 over x squared. That's why I use the terminology of constant. Now, if you multiply them, first let us find the pointwise convergence. Wherever it converge, so limit fix okay, let me also consider the domain and a equals 0, 1. So we are considering this function's convergence on this interval. So limit fix x in 0, 1, limit n goes to infinity. So fn x g of n x. So I'm just considering the pointwise convergence. Maybe let me note it. Pointwise convergence. Now what is this limit? Let me expand. Limit n goes to infinity. 1 over x, 1 minus 1 over n. Since x is independent of this variable n, so when you take the limit, everything is continuous constant because they are constant. This is going to be 0, so you end up with 1 over x. So it is pointwisely converging to the function of 1 over x. Okay. So let us consider, is it uniform or not? We have several ways to do it. First, we can calculate the supremum. So claim fn gn uniformly does not converge on 0, 1 to 1 over x. Method 1, proof 1, let me say. So consider supremum of this set. Fn gn fn x gn x minus 1 over x in 0, 1. So I can rewrite this supremum as supremum. I'm gonna just write this fn gn, right, which is this. So 1 over x, 1 minus 1 over n minus 1 over x in 0, 1. So this is equal to supremum. Maybe I'm doing it a bit slow, but I need to explain. 1 over x and x in 0, 1. As you can see, this is the multiplication of x and n when x in 0, 1. So this supremum is always increasing, not bounded. You can show that, okay? Because n is fixed, n is not changing here, okay? After finding this supremum, you need to take the limit. That should be approaching to the 0 if it is uniformly convergence. Remember this 3.1 in the previous question. So you can calculate the supremum is unbounded. So it means that since everything is positive, it's gonna be infinity or unbounded. Okay. So it means that it is not uniformly convergence. So proof 2. Let me move this screen a bit. Oops. Nasıl yapacağız? 2 parmak. Now consider the following sequence. So I want to prove my sequence. I want to find some sequence in terms of n inside x. Then using this sequence idea, I'm gonna show that this is unbounded. The similar idea, the proof one, but yeah, it is another method. Consider xn sequence equal to 1 over n square. So as you can see, this is, and starting from 2, this is inside this interval 0, 1. So it is in the same boundary. So what do? Is I have some fn's, right? Fn's, I don't care how it is. Fn gn's, right? And this is its graph. So I want to find a sequence on this graph such that it will prove it is not reaching to the same point or it is unbounded, etc. So now fn xn gn xn is just 1 over, since it is 1 over xn, okay, but not like that, okay. I need to also subtract from the uniform convergence, so 1 over x n. So this is equal to 1 over n square multiply n. So this is indeed equal to n. So we have found this thing, okay. Okay, look at this. This is the set, okay. So this is what inside of the supremum, right? We have calculated. This is just n. So when after the supremum, after the calculating the supremum, if you take the limit of this, it will just gonna diverge, okay? Let me just complete it. Okay. So I'm gonna use this epsilon delta idea or epsilon n idea. So given, okay, so for epsilon equals to 1, for any n in the natural numbers, this thing fn xn gn xn minus 1 over xn is just n is bigger than epsilon, okay, bigger than epsilon, which is 1. Since it is a bit dangerously close, let me choose this epsilon 1 over 2. Now it is fine, because every natural number, if we are disregarding 0, is bigger than 1 over 2. So for some epsilon and for some subsequence, we have found that it is not bounded by epsilon, okay. That is equivalent to saying that this is equal to saying that fn gn uniformly does not converge on 0 1 to fg, which is 1 over x in this case. Okay, let's look at our question first. Assume that fn approaches uniformly converges to f, gn uniformly to g, and there is some positive number such that for every x in the domain, these are bounded, okay, f and g are bounded by m. So in this case, despite the previous question, we have now a convergence, a positive result, okay. So we can prove this with the same classical strategy. First, let us start from our aim. Our aim would be at the end, this absolute value, fn x gn x would be less than f of x g of x, right? And we would have some fn x minus f less than epsilon for any epsilon, or gn x minus g less than epsilon. So we are going to use these two inequalities. Since it is very classical, we will add and subtract something like that. You can, okay, let me do it very slow. Okay, fn x gn x minus fn x gx plus fn x gx and minus fx gx. Okay, now I just add 0, right? We didn't change anything because they will cancel. So you can also write this as less than, by using the triangle inequality, of course, fn x g and x minus f and x gx plus f and okay, let me write fx, yo böyle yapalım, tamam. F and x g of x minus fx gx. Okay, let me also rewrite it. F and x g and x minus gx plus we have g of x f and x minus fx. Okay, I know that this is bounded by m and this is bounded for any epsilon in this case. Okay, so this is bounded and depend on epsilon, and it can be as small as possible, this part. Yeah, I mean this part's gonna approach 0 as we desire, because this is bounded. Okay, we are using this boundedness condition. So it's in the similar way, it is not that easy, but I'm gonna find some bound for fn2, because fn's are uniformly converging to f, and fx is bounded. So it means that these fn functions are bounded for bigger values of n. I don't say every fn satisfy this bound or some bound, but if you approach to f, I mean if you increasing in n, these things will be bounded, because from the calculus, if you remember, if you have some convergence sequence, it should be bounded. In our case, boundedness given by bounded by some constant for any x, not just for specific x. That's just a little difference, but I'm gonna show this is also bounded, so this is also dependent on epsilon, and I can make this part also as small as possible I want. Okay, now let me start from definitions. So first, this fn x can be written as like that. Okay, this fn x equals to f of n x minus f of x plus f of x, because I'm gonna use triangular inequality and boundedness of this f of x for any x. Okay, so this is by triangular inequality f of n x minus f of x. So this will be less than any epsilon, etc., and f of x, and this is less than m, right? This is less than m. So this is indeed less than f n x minus f of x plus some constant m. Okay, now since okay, no, let me just start the proof. Given any epsilon, so I'm just starting from this, and I'm gonna show this thing is less than epsilon. Okay, that's my aim. Since we have it's unnecessary, since f of n uniformly f for epsilon equals no, not equals, for some epsilon I'm gonna find okay, since okay, what is my aim? My aim is this is being less than epsilon, right? And this is equal to this, this is less than this, and this is less than this. So fn minus fx, my aim here. So this will be less than m. So if I choose this part is less than epsilon over 2m, because this is less than m, so they will cancel and I will get this part less than epsilon over 2. That's why I'm gonna write specific epsilon here, or version of epsilon, right? Because it is uniformly convergent. It should satisfy for any epsilon. This thing is less than epsilon. For epsilon over 2m, we have n1, let me say, in natural numbers, such that if n is bigger than n1, then f of nx minus fx is less than epsilon over 2m. Okay. Now, if you use this inequality, by the way, it is n, not 11. Now, if you use this inequality here, this would be less than m, this would be less than epsilon over 2m. So if you multiply these two bounds, they are positive, you will get epsilon over 2. This part is finished. Now let us analyze this part by using this new created inequality. Okay, if you plug this inequality instead of this one, okay, so you will get this fn, I mean this, is less than this thing. So by the way, we have fixed that. Okay, we have some inequality for this part, right, which is epsilon over 2m. So this will be less than epsilon over 2m. And we have another thing, m. If you just calculate this thing, epsilon plus 2m squared over 2m. Right? This whole thing is less than this number, whatever it is. And this number is bounding f of n. So, I mean, this is less than this part. So, similarly, I'm going to use the uniform convergence of Gn for some specific epsilon, probably this, so that at the end, if I multiply by them, by two of them, I will get desired result, right? So let us do it. Okay. Now, since G of n's are uniformly converging on A to G, for m over epsilon, let me also put epsilon plus 2m square, we have some natural number n2. By the way, since m and epsilon are positive, this thing is also positive, so this is a valid epsilon value, and for this value, since it is convergent, we have another natural number such that if n is bigger than n2, then g of nx minus gx is less than epsilon m over epsilon plus 2m squared. Now, so given any epsilon, we have created such inequalities. Okay, this was just a parenthesis. So I'm gonna find some number such that this is less than epsilon. Okay, now for n3, which is the maximum of n1, not mn, 1 and 2, if n is bigger than n3, or maximum of n1 and 2, we have now then f n x g n x minus f of x g of x, which is already calculated here, less than this thing, right? Less than this thing, is then less than, so first I'm gonna just write f of n's boundary, right, which is this thing, epsilon plus 2m squared over 2m, multiply by this boundary, which is here, epsilon m over epsilon plus 2m squared, right? The way that I define this boundary is exactly for the boundary of this, right? Because I want to cancel them out and I want to get epsilon over 2 for this part, because in the first case we have created this part is less than epsilon over 2. It was easy and it was more obvious, but here you need to calculate something. But if you know what you are doing, everything is fine. Now after that, plus this thing, g of x. What is the boundary of g of x? It is given, m. So it is m. Multiply. What is the boundary of this thing? We have just set, right, epsilon over 2m. Now it is easy. Let's do the cancellations. This m is gone. This part is gone. We have another cancellation, m. So we have just epsilon over 2. Okay, this is gone. Epsilon over 2 because everything else is gone. M is gone. Epsilon over 2. So we have just epsilon. By the way, another comment, for example, if you don't want to deal with these specific epsilons, if you found at the end epsilon multiplied by some constant, it is finished because you can choose epsilon as small as possible. That's why some constant multiplied 0 does not matter. So at the end, if you found epsilon multiplied by some constant, it can be messy, but it should be positive. Then it means that you are just proven. Okay, no problem. But if you want to do is as elegant as I did, you need to calculate some cancellation, blah blah.